Alright, so quiz 1 answer key. First one asks us for a mechanism of a Friel-Crafts acylation reaction. And so the first step would be to take the lone pair on the chloride and form our more reactive intermediate. And now we're going to lose AlCl4 minus. We're going to make this strange looking resonance stabilized intermediate. I'll try to draw this a little better here. And now this is my electrophile that's going to react with the ring. And I can take my ring. I'm going to substitute on the para position because I have an ortho-para director. And that gets me to that intermediate. We want to use resonance structures in this case to show the stability of this intermediate. So I'm going to draw two more resonance structures here, as you're probably very familiar with at this point. So there are my three resonance structures. And of course, there's an extra hydrogen right here. I'm going to use, actually I'll put it over here, it's a little easier to access. I'm going to use the AlCl4 minus compound as a weak base. Remove that H, reform the alkene, reforming the aromatic ring, and I would make this compound, which is my product. So this is an aromatic substitution. It uses the activated intermediate as we saw right here. We get a number of resonance structures showing the stability of our intermediate on the ring, and then we make the product in the para substitution pattern. You could also show the ortho substitution pattern just by choosing a different double bond to react with, but in this case the question said you only need to show one isomer. Next question asks us to identify whether we have aromatic or not aromatic compounds. Remember that aromatic need 2n plus 2 pi electrons. They need to be planar, and we need to have a series of p orbitals all around the molecule. So this molecule here, which has a CH2 group, does not have p orbitals, so this would be not aromatic. It is a ring. So they need to be ring, they need to be planar, they need to have p orbitals all around the ring. The one in the middle, I think, does have 7 p orbitals all around the ring. It has 2, 4, 6 pi electrons, which does match our number that we need to, so this would be aromatic. And the last one, the square, does have a ring, does have p orbitals, could be planar, but it only has 4 pi electrons. That does not match our number. In fact, that's useful for determining that this is anti-aromatic. It's not just not aromatic, it's actually anti-aromatic, which is even worse than not aromatic. The key for quiz 2, we're asked to provide the correct IUPAC name for this compound. We'll start numbering nearest the OH. We'll end up with a 4 for our OH group. We also have a methyl group on number 3 and 7. So 3, 7 dimethyl. I have 8, so I have octanol. And I have 4 octanol. And then I have 2 stereocenters. I'll outfit those in red here. Let's look at the stereocenter at number 3. Priorities would be the one with the OH, the shorter chain, and the methyl. That gets me S, 3S. And then let's look at the 4. Obviously the highest priority is the OH, then the branched carbon, then the straight chain carbon. 1, 2, 3 is clockwise, but of course the H is projected towards us. So that is also S. And that's it, I believe. There are only those two dimethyl groups, so 3, 7 dimethyl, 4 octanol, or oct 4 all, octan 4 all if you want to. I don't care either way. All right, so now we need to design a synthesis for this compound. We need to observe that we start with the OCH3, we put something on in the para and the ortho position. This is an ortho-para director, so that makes sense. So we just really need to decide what order to do these in. I think it's better to put the bromine on first because it's only weakly deactivating, and it will also block the para position from addition of the NO2. If we put the NO2 on first, we'll have an even slower reaction for the final one because we're putting this strong deactivating group on. So let's put the bromine on first. And then we just need to put the NO2 group on, which will go, again, ortho-para to the methoxy, which is exactly where it is. So that's as simple as that, just 2 steps there. Question 3. Which of these will have the fastest rate and draw the expected product for that reaction? So let's see, we have, what kind of director is this? This is a ortho-para director. This is a moderate activator. Chlorine is also ortho-para, but it is a weak deactivator. So I think fuming H2SO4 puts an SO3H group on, and I'll put that in the para position. Same thing here. Fuming H2SO4 puts an SO3H group on, but of course the more strong activator is the faster reaction. So in this case we have an activator versus a deactivator. The top reaction is the fastest one. We're asked to design a synthesis of these compounds, starting from benzene and any other reagents we want. So we should look at the first compound here. We observe a meta relationship between the 2 substituents. And we also have this weird chloro sticking on there. I'm not sure I know any way to put on the 2-carbon plus the chlorine substituent all at once. So we may need to modify the substituent after we add it to the benzene ring. So we need to keep that in mind. And we have a bromine on the bottom position. So which of these might direct meta? Well, the bromine is an ortho-para director. So that is not, we wouldn't put that on first because it's not going to direct into the meta position. So we probably need to install this 2-carbon sequence in such a way as to get a meta director that can then install the bromine meta, and then we can modify the 2 carbons into that chloro species. So I'm going to suggest that we use Friedel-Crafts acylation to add 2 carbons, because that gives me a functional group that it can be eventually modified to form a alkyl chloride. And then, of course, Br2FeBr3 can put the bromine on in the meta position. And I can turn this into an alkyl chloride by first reducing. To an alcohol. And probably some methanol there for a proton source. And then back up here, simply SOCl2 should give us the chloride. For the second step, or the second reaction, we need to make this bond, of course, if we're starting with benzene. This is an alcohol, and it's a tertiary alcohol, so we know that we can make tertiary alcohols via Grignards plus ketones. So maybe we take benzene, we turn it into a Grignard, first add bromine, then add magnesium, And now we can mix it with the appropriately shaped ketone, and we need to have a ketone that has obviously the O and then that many carbons, and I think there are 5 carbons in my red circle there, and I need a ketone on the second of the 5 carbons. So I know what shape my ketone needs to be. There are 5 carbons, the ketone's on the second carbon, and after protonation, which would be a second step, I think we get this product. So I don't need to draw that. So that would be question number 1. You could also use other means of doing this. Maybe you react it with an aldehyde and then add another Grignard to make your secondary alcohol after oxidation into a tertiary alcohol. But I think this is the quickest, most efficient way to get to that product. Here we have our roadmap problem. Just fill in the boxes, basically. So CH3Cl and AlCl3. That gets us to methyl benzene, or toluene. NBS will install a bromine on the benzylic position to get us to benzyl bromide. And then, of course, we're basically just substituting methoxide for our bromine for that last box. Next, we can go with the box in the middle here. Looks like we need to add a nitro group to our toluene, so that's just HNO3, H2SO4. Mix those together. We'll do that in the lab this semester. And then it looks like another Friedel-Crafts alkylation. After 5 years of this quiz sitting around, I'm not sure this will work anymore because the Friedel-Crafts alkylation needs to go on a moderately activated ring or anything that's not strongly deactivated. And we have a strong deactivator right here. Let's pretend that this moderate activator or weak activator is enough to counteract the strong deactivator effect. So if we add another methyl group, we should add ortho-para to our activating group, which would be right here, or on the other side, same thing. And in that case, I think I'm going to modify my product here. And the last step then is to, no, I'm sorry, I'm not thinking about this correctly. Obviously, ortho-para is right there. And the last step then is to reduce the NO2 to NH2. Zinc and HCl will do that reduction for us. Question 3 asks us to rank the following compounds in terms of acidity. We could remember pKa's, of course, and in that case we'd get about 9, about 16, about 18, and somewhere less than 16 because we have these electron withdrawing groups here. So we could rank them that way. We could also use areo. Atom is all the same. We have O for everything. Resonance. We have more resonance in phenol. So phenol should be the most acidic, and let's use a different color here. So phenol is the most acidic. And then I would have induction as my next one. This one with 2 chlorides should be the next most acidic. And then we know that bulkiness causes less acidity because the resulting alkoxide is less well solubilized by other solvents. So this should be 4, and this would be 3. Then we're asked to predict the products of these reactions. Lithium aluminum hydride with any carbonyl species will totally reduce all of them. So we'll have 2 alcohols as the product here. Excess Grignard should add methyl groups to both carbonyls. So there I have another methyl group on each of those carbonyls. Benzene plus looks like it's ethyl chloride and then KMNO4. So the first step here is adding an ethyl group. KMNO4 is a strong oxidizing agent. It's going to take any hydrogens at the benzylic position right there, oxidize the heck out of that alkyl chain and give us a carboxylic acid at that position. Remember that it doesn't matter how long this alkyl chain is as long as there's a benzylic hydrogen or two right here. Here we have acetoanilide actually. It is moderately activated because there's a lone pair right there. We've got AlCl3 and Cl2, so we're going to add that to a para position because this activator is an ortho-para director. So we'll put a chlorine there. You could also argue for a chlorine right here, perhaps if you wanted to draw that one, but I think the para is probably a little more likely because we have the large steric bulk right there. This next one is a nucleophilic aromatic substitution. We've got a strong base, strong nucleophile. We've got a good leaving group. And we have a good electron withdrawing group, the NO2. And so we're going to actually nucleophilically substitute the OH for the bromine. And lastly, we've got a Birch reduction. And so we're going to reduce this aromatic ring. And remember the differences between electron donating groups and electron withdrawing groups. This is a donating group, so we're not going to reduce at this position. We are going to reduce at these two positions that are up away from the donating group. So we should put our double bonds there, and you can see how we've reduced at those positions that are not next to the donating group. And lastly, well, actually number 5, circle the reaction scheme that is the best choice and give a one-sentence explanation of your reasoning. What are the differences here? We're starting with the same molecule. We're ending with the same molecule. Looks like we have the same reagents over the arrows, except that we've reversed the order in these two examples. So in the first example, we would put a nitro group on the ring first, and then add a methyl group. Second example, we put the methyl group on first, then add the nitro ring. Well, the nitro ring is electron withdrawing, it is deactivating, and it is a meta-director. So it doesn't look like it will put the methyl group where we want it. So I'm thinking that the bottom one is the right way to go. I don't think the top one would work at all, but if it did, it would produce that. The reason I don't think it would work is because once we've added that strong deactivating group, the Friedel-Crafts alkylation reaction does not work with strongly or moderately deactivated rings. So I don't think the top reaction would work at all. So we've got a couple arguments against it. You'd get a meta substitution, but it probably wouldn't work in the first place. Lastly, let's look at the product and the mechanism for this sodium borohydride reduction. So to start, I'm going to draw the BH4-, and I'm going to use my hydride as a nucleophile. Let's keep track of the newly installed hydride. Is right here. You don't have to do that, but it's useful, I think, when we're learning this. And then I have ethanol present. Just a proton transfer step. And that gets us to the product, which is simply the reduced aldehyde, which makes a primary alcohol. You'll notice that the alkene here was not affected by the reaction. Sodium borohydride does not reduce alkenes that are by themselves, so don't reduce the alkene there.